Have you ever looked at modern web security and felt like you were just completely drowning in an absolute alphabet soup of acronyms? I mean, think about it. JWS, JWE, JWK, JWA, JWT. It literally feels endless sometimes. But here's the reality of the situation. We live in a world where data is constantly being exchanged between systems that are implemented in completely different programming languages, built by entirely different teams, and managed by different organizations. So today in this explainer, we're going to decode the source material from Chapter 11 on the widely used JOSA suite of standards. We're going to discover exactly how these standards give us a highly reliable way to represent cryptographic algorithms, keys, and secured content using JSON. Okay, let's take a quick look at our agenda for today. We've got 6 parts. 1. The standards layer cake. 2. Algorithms and keys. 3. Signing data with JWS. 4. Encrypting data with JWE. 5. The JSON Web Token. And finally, 6. Security pitfalls and criticisms. We're going to construct our mental model of security layer by layer, starting from the basic metadata at the foundation, working our way up to complex web tokens, and then looking at where these implementations can go terribly, terribly wrong. Section 1, the standards layer cake, the basics of interoperability. So before we look at the individual pieces, we really need to understand the fundamental problem of interoperability. When security protocols like OpenID Connect or OAuth2 need to communicate, they have to exchange encrypted messages, right? To prevent the entire web from just breaking down with a million different custom formats, the JOSE suite enables interoperability by using JSON. Now, if we map out the relationships between the 4 core JSE standards, we can see exactly how they conceptually build upon one another to form this sort of security layer cake. At the very bottom, we have JWA, which identifies the algorithms. Above that is JWK, which represents the keys. Then, sitting right on top and utilizing both of those foundational layers, we have JWS for digital signatures and JWE for encryption. Understanding this dependency graph is absolutely crucial. Seriously, it's a game changer. Because when you understand how these data formats stack up, making sense of weird error messages from your security libraries becomes super simple instead of incredibly frustrating. Section 2, Algorithms and Keys, Foundational Blocks. Well, before we can even think about securing a message, we have to solve 2 very distinct problems: identifying the specific math being used and formatting the cryptographic keys. Let's tackle the math first. Imagine receiving an encrypted message over the wire. How does your system actually know which algorithm secured it? The source details that JWA, or JSON Web Algorithms, solves this simply by providing standardized string identifiers for cryptographic algorithms. And to accommodate new algorithms, these identifiers are registered with the Internet Assigned Numbers Authority, or IANA. So instead of guessing, a receiving application sees an identifier like HS256 and immediately knows, oh, I need to use HMAC with SHA-256. Or maybe it sees A256 GCM and knows it requires AES encryption using a 256-bit key in Galo/counter mode. It's brilliant because it removes all the ambiguity from the exchange. Okay, now for the keys. Cryptographic algorithms obviously take various keys as inputs. In closed, isolated systems, you might just store a key as a hex-encoded string in some random configuration file. But that doesn't scale. It doesn't scale across multiple teams and organizations. Enter JWK, or JSON Web Key. This is a standard for representing complex cryptographic keys as beautifully formatted JSON objects. It scales incredibly well, and it easily handles complex keys that might have multiple mathematical components, like elliptic curve keys. Crucially, JWK includes a standard field called the KID, or Key ID. This uniquely identifies the key, ensuring the receiving application pulls the exact right key out of its vault to process the incoming data. Section 3, Signing Data with JWS. Protect from tampering. Moving up to our middle layers now, we introduce JSON Web Signature, or JWS. This is the mechanism we use when data needs to be protected from tampering, and we need to prove its authenticity. But, and this is key, the contents don't necessarily need to be kept secret. The anatomy of a JWS object is strictly split into 3 distinct parts: the header, the payload, and the signature. The header is just a JSON object describing the cryptographic algorithm used. The payload is your actual data. It could be JSON, but it can actually be any arbitrary sequence of bytes. And finally, the signature ensures the header and payload weren't tampered with in transit. Now remember this critical takeaway: a JWS payload is always readable by anyone who can access the object. I repeat, it does not hide your data. So, how do we actually create one of these things in the real world? JWS objects are typically sent in HTTP headers or URLs, and we all know those are incredibly picky about allowed characters. To safely travel through these channels, we take our JSON header and payload and encode both of them using base64 URL encoding. Then we simply concatenate them together with a dot. Next, we compute the signature on that combined string. Base64 URL encode that signature and append it with another dot. The end result? You get the single, massive, URL-safe string with 3 parts separated by 2 dots, perfectly prepared for HTTP transit. Section 4, Encrypting Data with JWE. Adding confidentiality. While JWS guarantees our data hasn't been altered and proves who created it, what if our payload contains highly sensitive secrets? Like personal data or internal system IDs. In that case, we need to add a layer of confidentiality using JSON Web Encryption, or JWE. Now notice the significant difference in anatomy here. While JWS has 3 parts, a JWE object requires up to 5 components. We have the header, just like before, but then we add an optional encrypted key, an initialization vector to randomize the encryption, the actual encrypted payload ciphertext, and finally an authentication tag. Once again, all of these parts are base64 URL encoded and separated by dots. Oh, and it's definitely worth noting that if you're using direct encryption with a pre-shared key, that second component, the encrypted key, might actually be omitted. That's why you might sometimes see a JWE string with 2 consecutive dots in it. So the absolutely crucial point here is contrasting these 2 middle layer standards. JWS provides integrity and authentication. It leaves the payload completely readable to anyone. It acts kind of like a tamper-evident seal on a transparent envelope, right? You can see what's inside, but you know if someone messed with it. JWE, on the other hand, provides integrity, authentication, and confidentiality. It locks the payload in a cryptographic vault so prying eyes absolutely cannot read it. Knowing when to use which is a fundamental responsibility of literally any developer building secure APIs today. Section 5. The JSON Web Token, combining the layers. We have finally reached the frosting on our layer cake. This is where we combine all these previous layers into JWT, the ubiquitous standard used by massive single sign-on protocols like OpenID Connect. Now, it's super common to confuse JWT with JWS or JWE, but the relationship is actually quite simple when you break it down. A JWT, or JSON Web Token, is simply a JWS or a JWE with one strict mandatory rule added on top. The payload absolutely must be a JSON object. Remember how JWS and JWE can carry any sequence of bytes? A JWT cannot. It has to be JSON. Furthermore, this JSON payload contains standard fields called claims. For example, a claim called sub is standardized to represent the subject, meaning the ID of the user to whom the token belongs. Pulling back to view our complete mental map, we can see the entire JSOE and JWT ecosystem in one awesome view. JSWA and JWK form the base, providing the algorithm identifiers and the key formatting. JWS and JWE do the heavy lifting of signing and encrypting the data. And sitting cleanly at the very top is the JWT standard, defining the specific JSON claims needed for modern web authentication, riding right on top of the secure delivery vehicles provided by JWS and JWE. The whole shebang in one elegant stack. Section 6. Security pitfalls and criticisms. Risks in the real world. All right, before we wrap up, we really have to pivot from the theoretical mechanics to real-world application. Because as brilliant as this layer cake is, these highly flexible standards carry a massive, notorious risk. I really want you to ask yourself, does relying on a complex, heavily standardized alphabet soup automatically guarantee your application is safe from hackers? The harsh reality? No. No, it does not. The main criticism of the JSON and JWT standards is that they provide way too many configuration options. And as we know in tech, too much flexibility in a security standard leads to complex implementations. Complex implementations lead to devastating security vulnerabilities if developers aren't paying incredibly close attention. Case in point, the source material highlights arguably the most infamous vulnerability in this entire ecosystem, the alg none vulnerability. Get this. Under the official JWS specification, it is perfectly legal to set the algorithm field in the header to none. Yes, you heard that right. So if an attacker intercepts your JWS object, they can maliciously change the header to say alg none, modify the payload to give themselves admin privileges, and just forward the request along. Because none is technically a valid option in the spec, improperly configured security libraries will blindly accept the unencrypted header, skip the signature validation entirely, and just accept the tampered payload. It's wild, but it happens. Which brings us to our final and most important takeaway today. You must immediately ensure that your implementations and the third-party libraries you rely on are explicitly configured to reject none as a valid algorithm option. This flaw is extremely well known, yet it continues to compromise systems because developers just assume libraries are secure by default. Never assume. So you now understand the layer cake, from the algorithms all the way up to the web tokens. But ask yourself, if an attacker intercepted your tokens today, would your system's frosting hide a critical flaw, or would your vaults hold secure? Thanks for joining this explainer, and keep building securely.